When you hear the word wave, you might think of this. Waves have an everyday meaning, but also a specific meaning in science. Even so, water waves can tell us a lot about the science of waves. A light breeze ripples the surface of the water. A pebble thrown into a lake creates ripples. In each example, there is something disturbing the water, and it is the energy from that disturbance that creates the recognizable pattern as it moves through the water. If we bounce a rubber ball into the surface of a pond, we can set up a regular pattern of waves, and the pattern can be represented mathematically. Using a graph, we could represent the wave height on the vertical axis and distance on the horizontal axis. We can graph this pattern from another perspective too. If we pick a point along the surface of the water, we can plot the height of the wave on the vertical axis in relation to time. To make that clear, imagine we place a tiny rubber ducky on the water and watch it closely. We see the duck bobbing in place, its height moving up and down as time passes. In this wave model, we're charting the displacement of the water. Once we have this mathematical model, we can explain and predict more complicated waves. For instance, when two waves interact in the water, the result is a more complex pattern. By superimposing a chart of each wave and adding together their displacements over the same time intervals, you can graph the more complex wave pattern. Waves, like the ones we see in water, are a fundamental pattern seen everywhere in nature. For instance, music is created by complex waves traveling through air. Earthquakes and tremors are caused by disturbances that propagate through the Earth's crust. And electromagnetic energy moves through space as waves. In fact, waves are universal. We can even find them traveling through the fabric of space-time. We call these gravitational waves, and in some ways they are quite similar to water waves or sound waves.
In water, if you talk underwater, somebody else can hear you because the sound gets transmitted through the water. So gravitational wave is literally the same kind of wave. It's the sound wave of space itself. So that as it travels through space, it shrinks space in one direction and stretches it in the perpendicular direction as it's moving in the other direction.
When Albert Einstein predicted gravitational waves over 100 years ago, he pointed out that these waves would be so faint that we could only dream of building a detector sensitive enough to detect them.
The calculations Einstein did indicated that no matter how good an experiment we did, we would never ever see these waves. They were just so weak.
Although it took nearly 100 years, researchers have now built detectors just sensitive enough to hear the largest of the gravitational waves moving through space. The detectors rely on laser beams reflecting back and forth down two perpendicular tunnels 4 kilometers long. A passing gravitational wave alters the length of the tunnels very slightly, and that change is detected by the laser beams.
So if I'm sitting here and hear the two LIGO arms, as the wave goes past, this arm will shrink while that one is stretching, and then this one will stretch while that one is shrinking, and these will oscillate. Okay? So you have to see this combined signal that tells you you have a gravitational wave.
Even though any accelerating mass creates gravitational waves, current detectors can only sense waves caused by large masses undergoing huge accelerations.
So not only did they detect gravitational waves, if you ask what caused them, it was two black holes, and these two black holes were orbiting each other, and as they orbited, they were emitting gravitational waves and energy, and as they spiral inwards, they eventually merged. And the last gasp of that spiral emitted the brightest pulse of gravitational waves, which then traveled through space for 1.3 billion years. This was 1.3 billion light years away from us, this happened, and then traveled right through the LIGO detector, and we saw the signal just after the detector was switched on. A completely unambiguous confirmation of Einstein's theory.
The ability to detect gravitational waves has opened up a whole new way to explore the night sky. Events that would otherwise be invisible to us, we can now detect through the faint whispers of their gravitational waves.